Well, all right, everybody. We got a lot of empty chairs, but I'm going to go ahead and get started anyway. Hopefully, everybody's finding parking and getting themselves up here. Welcome to a Thursday. I hope that your day is off to a good start so far. It's nice to have you all here. Um, Quick reminder that as you turn in these homework assignments, I do publish the solutions to those assignments. And because my grader is not able to grade every problem in detail, even if you're getting a really high score on the homework, even a perfect score on the homework, it's still a good idea to confirm that you're doing everything correctly. So those solutions are there for you to look at. Or if you did struggle with anything on the assignment and you didn't have a chance to ask me about it in office hours, then that's sort of another option for you, which is to just go to Canvas. There's a folder called Homework Solutions in there, and you can check up on those solutions. We've had 6 homeworks so far. Number 7 is due tomorrow night. It's a pretty fast assignment, but I'm actually going to probably end up doing a couple of the problems from the assignment today during class as well. There's one on the board already over here, and I've got a couple others I was just going to do anyway. So it should make it pretty easy for you. The big thing coming up on our radar, of course, is the midterm. I talked about it quite a bit on Tuesday in class. And over this coming weekend, I hope that you guys will take some time to start studying for that. In fact, tomorrow is actually a campus holiday. Even though this homework is due tomorrow night, I am still going to have office hours. Because I want to be available on the days the homework is due. So technically the campus is closed, but you can still come to my office hours either in Zoom or you can drive up and you probably get a front row parking spot. There won't be a lot of people around, I don't think. So it'd be a good chance to ask me some questions if you have any, either about the homework or if you want to, just get an early start on studying for the midterm. Tomorrow's going to be a relatively quiet day around campus, and I will be around. So feel free to check in with me if you'd like to about that. I think those are really all I have for announcements. There will be an assignment for next Tuesday as well, but there will not be a lot of a big lecture next Tuesday. So I'm going to have more time next Tuesday to probably do a lot of that assignment with you and for you. So don't stress out about the homework for Tuesday too badly, because next week on Tuesday, we're going to do a bunch of it here in class. So that should hopefully take a bit of the pressure off. The big thing is to start digging into that resources folder that I showed you on Tuesday in class. So I try to get a look into that so you can not be cramming at the last minute on Wednesday night for the test. That's my hope for everybody here. Okay. Any questions about any of that? Okay, so right now it's just the homework due on Friday and then the homework due on Tuesday. Oh, I also forgot to mention, I think almost everybody now has stopped by my office to do a quick intro. And for everyone who has, I am going to be sending out an extra credit quiz that you'll be able to earn points towards your midterm. I'll probably send it out over the weekend. So just be watching your Canvas email, because I'm only going to give you like a day or two to take this quiz. You can just do it, in whatever time frame is good for you. It shouldn't take you that long. It's just a quiz. But I just wanted you to know that is coming. For those of you who have stopped by at least one time to say hello, you will be eligible to earn, probably it'll be something like 3 points of extra credit towards your exam next week. It'll just be points added to your score. Okay, so that will be also on the horizon. All right, well, if there's no other questions about anything sort of logistically or administratively, I'm going to get right back into the math today. Super stoked about this. Up with determinants, right? That's my advisor's motto, and it's my motto as well. I think they're really cool. They're really awesome, and there's a lot that we can learn from them and get from them. But in order to take full advantage of that, we have to know how to calculate the determinant of a matrix. It's only going to work for a square matrix. So notice it's an n by n matrix throughout this whole conversation. And sort of I gave you some simple formulas for 2 by 2 and 3 by 3 determinants on Tuesday. But ultimately, the end-all be-all of determinant formulas is the one that's in the cofactor expansion theorem, which I've rewritten on the board again here today. Now, this theorem is a little intimidating when you just read it out because of the double subscripting everywhere, but it isn't that hard when you're actually applying it on a problem in practice. The idea is you're going to pick any row or any column of your matrix. It actually doesn't matter. You'll get the right answer for the determinant of A regardless, okay? So you can pick any row or any column of your matrix, and you're going to do cofactor expansion along that row or column. Now, what these formulas are telling you to do is to simply add up across the row or down the column, add up the entries of that row with the cofactors from that row. So you're multiplying, right? AI1 times CI1, and then plus AI2 times CI2. And you're going all the way across row I doing that, right? Or if you prefer, you can also cofactor expand column-wise. So you can pick a column and take the entries from that column times the cofactors from that column and just go adding up all those terms all the way down. Okay, so it's your choice. It's your choice which row or column you want to use. And again, this is mostly relevant if your matrix is 4 by 4 or larger. Because again, if the matrix is a 2 by 2 or a 3 by 3, we got simple formulas for the determinants in those cases. So this is really going to come into play mostly when n is 4 or more, okay, for larger matrices. How do you calculate the cofactors again? We went over this on Tuesday, and we're going to practice it again in here in a minute. You just take the determinants of the submatrix of A that is obtained by deleting row I and column J. This is called the minor, the Mij. That's the minor associated with I comma J. You take that minor, guys, and you sometimes do a sign change on it, right? So to get the corresponding cofactor, you just take the minor and then you do a plus or a minus. The plus or minus just depends on the I and the J. And if you don't want to remember that formula, I gave you a little secret way of remembering it on Tuesday in class. I sort of said, you can just start with a plus sign in the upper left corner and then alternate plus minus to whatever position in the matrix you're looking at, okay? And that's how you can remember when you need to do a sign change, okay? So what I'd like to do is actually do a full-blown example of using this cofactor expansion method to find a determinant. I've got a matrix on the board here for you guys. It's a 4 by 4. So remember, with a 4 by 4 matrix, we don't have an arrow method. We don't have any other really nice shortcuts for this determinant. So we're going to have to do this one sort of full blast with the cofactor expansion approach. So far, so good? So let's try it. I want to find the determinant of this matrix using cofactor expansion. And remember, I can do that expansion on any row or any column that I want. Does anybody have a recommendation? Is there a preferred row or column that might make my life a little easier here? Row 3. Why do you say that, Yair? Because of these zeros, row 3 is going to be a lot easier to evaluate. Let me write it out so you can kind of see what I'm talking about. So for the solution, and I like to tell people what I'm expanding. So I'm going to expand row 3. I like to put that into the notes so we can see what we're doing. And if I do that, if I expand on row 3, that would be I equal to 3. If I look at my formula here, then we're supposed to do A31, C31 plus A32, C32 plus A33, C33, and then plus A34, C34. That's how it would look written all the way out. Okay. But here's the deal, guys. Here's the deal. A31, the 3-1 entry of the original matrix, is actually already 0. Right? And so is A33. A33 is also already 0. Okay? So I actually only have to do 2 terms. A32 was 3. So it's 3 times C32, and then plus -1 times C34. So I've just put in the A values there from that third row. So far, that's what I've done. Now, can I give you a little suggestion here, a little hint on dealing with this? I don't like to have to remember the sign change thing at the end. So what I will usually do, and I recommend you do this as well, is if a sign change is called for, I like to get that embedded into my work right away. So I can see right away that C32, 32 is right here. That is a negative position in the matrix. There should be a sign change. So what I like to do, guys, is I like to incorporate it right now. Before I even do this particular term, I just want to do a sign change on that minor. So the C32 will be the negative of M32. And what about C34? Is that going to have a sign change as well? 3, 4 is actually right here. Again, 3 plus 4 is odd. Odd numbers, when you have -1 to an odd power, there's a minus sign in that. So there will be actually another minus that comes into that term. Okay? So what we're going to get here, guys, is -3 times the 3-2 minor. Now let's write down what that would look like as a determinant. So remember that what we have to do for the 3-2 minor, we're going to delete row 3 and column 2. And we're going to take the determinant of the smaller matrix that's left over after I've crossed off row 3 and column 2. Let's put the rest of the matrix in here, guys. Row 1 has a 1, a 3, and a 4. The second row, -1, 5, and -2. And the third row is 2 and 1 and -3. Okay, so I'll go ahead. That's going to be the submatrix that's going to give me the minor that I'm looking for. Okay, and then let's keep going. Notice that these 2 negatives actually just cancel. And so you're just left with the M34 here. So this is going to be another determinant. But for M34, now I'm going to cross off row 3 and column 4. So it's a different 3 by 3 submatrix. So if I've crossed off row 3 and column 4, I'll get 1, 2, 3, -1, 1, 5, and then 2, -2, 1. Just like that. And what we've got here, guys, is a couple of 3 by 3 determinants to do. But it could have been 4 of them. If we had picked a bad row, or column to expand on, we might have had to do 4 terms right now. So actually doing 2 terms doesn't really seem that bad to me. Remember that for a 3 by 3 matrix, we can do the arrow method to find these determinants. So I'm going to do that. Let's just remember how that worked from Tuesday. I recopy the first column and the second column just to the right of my matrix here. So remember how that works. So just recopy the first 2 columns. And then I'm going to draw my arrows. So I actually need a little bit more room. So -3 is going to get multiplied by, let's do our arrow method. 1 times 5 times -3, that's -15. Plus the next diagonal is 3 times -2 times 2, which is -12. And then plus the next diagonal is 4 times -1 times 1. Well, that's -4. So all of those are with plus sign, right? Those are all with plus. And then we have to, I think on Tuesday I used red for the other arrows. We have to do these diagonals going the other way. 2 times 5 times 4, that's 40. But remember that the red ones are getting subtracted. So minus 40. And slow me down if I'm making any mistakes. It's still early for me. Okay. And then if I shift to the right, 1 times negative 2 times 1, we're subtracting negative 2. Right? And then the last arrow is negative 3 times negative 1 times 3, which is actually 9. And we're subtracting 9 on that one. Okay, so far so good. That's the arrow method on this little 3 by 3. Remember, there's a factor of negative 3 that's out in front of that whole thing. Now, in a minute, I'll come back and clean up these numbers, but let's write down the other term. So the second one here, we have another 3 by 3 determinant to do. Actually, I think we did this one already on Tuesday, but I'm going to just calculate it again. The first 2 columns get recopied just off to the right of my matrix here. And I'm just going to take my first arrow as a 1. And my second arrow is 2 times 5 times 2, which is 20. My third arrow is 3 times negative 1 times negative 2, which is 6. And then I have to start doing my arrows the other way. 3 times 1 times 2 is 6. That's with a minus. And then we have negative 2 times 5 times 1. So that's minus negative 10. And then 1 times negative 1 times 2 is negative 2. So just be careful with some of these double negatives that happen. You do have to be a little careful with that. Okay? So far, so good. Now I just have to crunch the numbers on this. Actually, if this was on a test and you left the answer like this, I'd probably be just totally fine with it, right? So this is, the rest of this is literally just algebra. That's not really too interesting. Negative 3 gets multiplied by all of this. We just have to be a little careful here. Let's see, negative 15 plus negative 12 plus negative 4, that's negative 31. I subtract 40 from that, it's negative 71. And then subtracting, I guess, another 7 essentially. So 71 minus 7, 78. So I think it's negative 78, if I'm not mistaken, for that part. And then plus this one, which actually we did on Tuesday. 6 minus 6 goes away. Just 1 plus 20 plus 10 plus 2. That adds up to 33. Okay, so we work this out. 3 times 78 is 234. And to that, we're adding 33. Just doing a little number crunching this morning. And that comes out to 267 as the final answer. That should be the final answer. Remember, the determinant is just a number. Any questions on that? Please, Dari.
Can you repeat one more time why you did the double negative 1?
So there's already a negative 1 because of the A34 value here. So she's asking me, why is there 2 negative 1s right here? So there's already a negative 1 from the A34 entry. And then the cofactor that goes with the 3-4 position also picks up a -1. So I like to write them both down. They end up canceling out, as we see. Yeah, good question. Anything else on this?
So when you're, that's the cofactor expansion, or what's the little thing called?
This is a cofactor.
No, the one on the left.
This is just my little diagram to remember when to do a sign change.
Oh, okay, so
It doesn't have a name.
it doesn't matter whether you start with plus minus or minus.
Oh, no, you have to start. This is always a plus in the upper left corner.
Okay, okay.
So, and you can tell from here, I plus j equals 2 in the upper left corner, which is an even number. So
Okay.
yeah, you start in the top left with a plus, and then you just alternate from there. You can't mess it up. It's pretty impossible to mess up this diagram. Caesar.
Silly question, bro.
That's
Why
okay.
the 3? In
This one?
Yeah.
This 3. So that is actually this number, sorry. So I kind of got off kilter here because of those zeros. A32 is this number right here. Yeah.
do you need us to write the first two columns on the right side of that matrix in order to be able to follow our work during the exam?
No, so I was really, really detailed here. If you get good at this and you're comfortable sort of just going straight to this, I would be okay with that.
I mean, like when we get to that part, the little guide you showed us with the first two rows.
Oh, this thing,
columns,
the
yeah.
2 columns here?
Do you need that to be able to follow our
Nope.
work? or-
Nope, I don't. If you just write down the 6 numbers there, I'm good with that too.
Okay.
Yeah. Actually, after a while, you sort of get good at this and you start to realize you don't really even need to draw the first 2 columns because you can figure out which numbers are being multiplied. Yeah, there's a little pattern to it. But just in the beginning, I kind of like to be super detailed, write it all out. If anybody needs more practice on determinants, I have a suggestion for you. Try any other row or column. Besides, we just did row 3. Try any other row or column. You already know what the right answer is supposed to be, right? It's supposed to be 267. The numbers along the way will be completely different. But at the end of the day, when the dust settles, any other row or column should give you 267 for the answer. So you could try that. If you just need more practice, you now have an answer key for what the determinant should be using any other row or column. Oscar. You must be reading my mind. That was the next thing I was going to say is, so what does this number mean? What is the point of it? Well, let me ask you one question. Do we know if this matrix is invertible or not?
No.
Yes.
It is invertible because, as we said on Tuesday, a matrix is invertible if and only if the determinant is not 0. So I would like to write that down. So just as a little remark, here, since the determinant of A is not 0, we know that A is invertible. So we know that because that was one of the sort of the motivations for this. But what it's Oscar, right? What Oscar is asking me is a little bit deeper question than that, is like, does this number actually mean something? Like if this number had come out to be 266, would that have been any different than getting 267? After all, it's still non-zero. The matrix would still be invertible. So does the number itself actually mean something? Is there some value in the number itself? The answer is yes, there is a geometric insight that we can get from this number. And there's actually some other applications of it as well. In a little while, I'm going to actually show you guys that we can actually find the A inverse without doing EROs. Do you remember that Gauss-Jordan method that I explained a lecture or two ago? A lot of EROs, right? You gotta be real careful with. Turns out there's an alternative way to find A inverse that does not involve EROs at all. Instead, it involves determinants. And this number would play an important role in coming up with that value. So I'm going to come back to that. I'm going to come back to that in just a little while, a little bit later today. Okay. But for the time being, the purpose of this warm-up problem here, guys, was just to see, do we can we execute this cofactor expansion method? You're allowed to use this method, by the way, even on a 2x2 matrix, even on a 3x3 matrix. So if you don't like the arrow method here, you don't want to use it, no sweat. You can use cofactor expansion on any matrix. And it's always going to be legitimate. Okay. Anything else on that? I want to do one more example. Let me put it here. You guys think we could handle a 5x5? Before you agree to that, let me point out that you're going to expand a row or a column, right? Each one of those rows will have 5 entries, and each minor will be a 4x4 matrix. So that would be, in other words, you would have 5 problems that are about this amount of work. So I'll ask you again, do you think we can handle that? Sounds kind of rough. Okay, nobody's doing anything else today, right? You have the whole day off, so, all right, so I think we can handle, let's try one. Let's try a 5 by 5. Double dare myself, okay? So let's find the determinant of A, where A is this matrix right here. I'm gonna give you this matrix. 3, 6, 8, 9, 5. It's the first row. The second row is going to be 0, -2, 8, 7, 6. And then on the third row, I'm going to have 0 and 0 and 5 and 1 and 2. And the fourth row is going to be 0 and 0 and 0 and 3 and -4. And the last row is going to be 0 and 0 and 0 and 0 and 1. So there is my 5 by 5 matrix. So as advertised, if I want to solve the determinant of this by using cofactor expansion, I have to choose a row or a column. And obviously every row and column has 5 entries. So there will be 5 terms to my standard cofactor expansion formula over here, and each of those terms has a cofactor in it. So we are going to be looking at 5 cofactors, but each cofactor is going to be a 4 by 4 submatrix. So we're going to be doing 5 4 by 4 determinants. On this warm-up problem, we just did 1. Now we're going to do 5 of them. Unless you guys can be really smart about it with me and give me really good advice about how to do this, I really hope you do. Which is, would somebody like to suggest a good choice of a row or a column to expand along? What is your name again? Ryan? Yes, go ahead. Row number 5 has a lot of zeros in it. I love it. Or you could have said column 1. That would have been good as well. Yeah, so let's try to expand row 5, okay? And if we do that, we can write down the determinant form. I'm gonna go a little faster on this one. So
I thought you were already going fast.
I'm gonna go a little faster. So this entry here has a plus on it. So that's 0, and then see, this will be a minus, plus, minus, plus. If I look at row 5, these are the plus minus pattern of row 5 on my little alternating terms. So, you know, it's the first entry has a 0 on it though, right? And the second entry technically would be negative, but it's also minus 0. And then the third entry would be back to plus 0. The fourth entry would be back to minus 0. You're alternating plus, minus, plus, minus, plus. The last one is a 1 with a plus on it. It's a 1 times, so this would be 1 times C55. If we want to use the cofactor notation, that would be the 5, 5 entry right there. And how do we find C55? We cross off row 5 and column 5. Leaving us with this 4 by 4 matrix right here, yeah? So this C55 is just, and I don't want to write it all out, but the 4 by 4 determinant there is what you'd have to now calculate. Can somebody suggest how would be a good way to do the 4 by 4 determinant that we see here? Expanding on what?
The row 4.
How about row 4 here on this 4 by 4, right? Because in the fourth row, I have a ton of zeros, right? So let's just write down what we have. We have a 1 from right here, and then times, if I go along row 4, this time I'm not going to write out all the zeros. I have a 0, minus a 0, plus a 0, and then, actually, I take that back. So let's look at this 4 by 4 and look at the plus minus pattern. This is a minus in row 4, minus plus on row 4. So it's really minus 0, plus 0, minus 0, plus 3, times C44. Okay, but C44 is, again, if I cross off row 4 and column 4, I'm going to be multiplying by just the determinant of this 3 by 3. Okay, so yeah, I guess I can just leave. I don't need to. Sorry, let's just go to the next line here. So let's work out what is the C44? In other words, what is the determinant of this 3 by 3? Well, you could use the arrow method now, but actually I'm going to just keep running with the cofactor expansion. For this 3 by 3, what would be a good choice of a row or a column that we could expand along? Row 3. Row 3, right? Is that what you're going to say? So row 3, and notice it's going to have a 0 and then another 0, and this 5 is going to be with a plus. So 5 times C33. Okay. Well, so far I've got 1 times 3 times 5 times C33. C33 is the determinant of this 2 by 2 because you cross off row 3 and column 3, you're left with this little 2 by 2. And if you do that 2 by 2, so this is 1 times 3 times 5, what is the determinant of this 2 by 2? Now I think I will just cop out and use the 2 by 2 determinant formula. It's A times D minus B times C, right? The little 2 by 2 determinant. So it's going to have a -2 and a 3 on it. And that is the final answer, which we could simplify to -90. It would be -90 for an answer. Question, yes.
Use the fact that it's upper triangular.
Yes, so this was way more work than you need to do. We actually have a theorem here, guys, and this is why I've kind of been speeding this up because I just want to get to the theorem. You don't need to do all this stuff, really. I was just trying to play the game with you on this example. To think, oh, this is going to be horrible. 5 4x4 cofactors. That sounds terrible. But actually, if your matrix A, which is n by n, is upper or lower, it works the same way for lower, triangular. So keep in mind, again, guys, this is what's called an upper triangular matrix. It's an upper triangular matrix. If your matrix is upper or lower triangular, then here's what I want you guys to know. The determinant of that matrix is just, so you can ask, where did these numbers come from? Well, the 1, the 3, the 5, the -2, and the 3, they're literally just the numbers on the main diagonal, and that is the theorem. This is A11 times A22 times A33 and times ... all the way to ANN. So you just, for a triangular matrix, you just have to multiply the diagonal values, and that makes it really easy to do the determinant of a triangular matrix, upper or lower, actually. That make sense? Any questions on that? So for triangular matrices, boom, we should have the answer really fast. I think there is a homework problem for Friday that is I think it's a 4x4 triangular matrix. You'll have that problem done in 10 seconds. It's really, really quick. That's for triangular matrices only. Yes, Caesar.
So how long do you suppose a 5x5 would take us with no zeros, stuff like that?
How long would it take to do a 5x5 with no zeros? I could put it on the test if we could test out that theory. Actually, it would be a heck of a lot of work, right, to do it by hand. But I actually am, so let's actually, I want to pursue that for a second. If I gave you a 5x5 matrix that had no zeros in it at all, does anybody have a thought about what we maybe could do with it other than deal with a horrendous cofactor expansion? Joel? how about doing some EROs on that matrix? Even if there's no zeros to begin with, what if we were to do some EROs on that matrix to bring it into a triangular form? And after all, we learned how to do that already, right? In the last chapter. This is something we know how to do. So that is a really good idea. Take your original matrix, do EROs on it to get it to be triangular. Then you'll know in a snap of the fingers what that determinant is. Super, super good, right? There's just one problem with that.
Don't you think that also by doing euros, you're gonna do a couple of steps just to get in that form?
Yeah, so there's the work involved in doing EROs. That's one negative. The other thing I want to point out is that as it turns out, when you do EROs on a matrix, you actually mess up what the determinant is. So like if you decide you're going to start tinkering with it, doing some EROs, you're actually changing the determinant. So that by the time you actually have your triangular matrix and you come up with your number here, turns out it's probably not the right number anymore because it's been changed through the EROs that you did. That's the bad news. But the good news is that the EROs will change the determinant in ways that are predictable. There's actually some properties that we can get familiar with, and then we'll know, okay, well, if I did this ERO, then here's what will happen to the determinant. And I can kind of do some bookkeeping with that, just keeping track of which EROs I did, what effect they would have had, and sort of trace that through my work so that I can still take advantage of this idea that Joel gave us, which is that, yes, we're going to try our best to do EROs to bring zeros into the matrix. So the strategy that I'm talking about for finding the determinant of A, so now I'm giving you sort of an alternative to the cofactor expansion method. So you don't want to do cofactor expansion? No problem. You can do EROs instead and get it into a triangular form. So use EROs to introduce more zeros into the matrix. So to try to get more zeros, the ultimate goal would be to make it triangular. That'd be like the best case scenario. So we're going to try to use EROs to introduce more zeros into the matrix so that it looks kind of like the one that was on that example over there. But the question we have to address is, how do the EROs affect the determinant of a matrix? Unfortunately, this is something we have to talk about now. We have to talk about this one. How do they affect it? But as I said, these are going to have predictable effects on the determinant. And so as long as we know these properties, we're going to be good to go. So let's say that we take the matrix A and we permute two rows, I'll say the ith and jth rows, to get a new matrix B. The question you might have is, well, how are the determinants related if I've permuted two rows? And the answer is that the determinant of B will pick up a minus sign. It will pick up a minus sign. So if you permute two rows, that's fine, but you have to insert a minus sign into the determinant. Now, if you do this more than once, if you do permutations multiple times, then of course you will pick up multiple negatives, right? So you just have to keep piling them up and keep track of this as you go along, all right? So that's the first one. The second one, if I start with A and I multiply, let's say, the ith row by K, remember this is our second ERO that we learned. So we multiply a row through by K. This one is also very natural. It's very natural. The determinant of the new matrix after you've multiplied a row by K is just K times the determinant of A. So it just picks up that factor as well. Doesn't that just make sense? Like if you multiply the third row of your matrix by K, then these A 3, 1, A31 will become KA31. A32 will become KA32, KA33, and KA34. Well, that K just gets factored out. So you're getting a factor of K that sort of comes out into the front of the formula, which is pretty reasonable.
Let's say you wanted to count up all your positive or your negatives when you're permeating.
Uh-huh.
Even though they're at different steps of your EROs, it's fine if you do that all together.
It is, yeah, you can pile up the results of these if you're doing several of these EROs, you can kind of wait till you're all the way done and then say, okay, let's just see what were all the things we did and just kind of pile up the effects of those, yeah. And we're gonna do an example of this in just a minute. There is one more ERO that I want to add to my list here. We can start with our matrix A, and then we have this adding operation where we do Aij of K. So we add a multiple of one row to another row to get a new matrix again here. And this is a slightly harder ERO to implement. I think people usually find it a little harder, but the good news is actually this is the one that has no effect on the determinant. As it turns out, the determinant of B does not change. So if I add a multiple of one row to another, the determinant just stays the same. That one is a completely safe thing to do. Okay. So you could write out some small matrices and kind of just test out these formulas and do these EROs, and you would see that they do work. I'm not going to really spend a lot of time now on kind of fully going through each of those. But what I would like to do is try out the strategy. That strategy at the top, I want to actually do a problem where we apply this strategy. And it's not going to be a very big matrix here. I'm just going to use a kind of a small example. Let's do an example here. It's only going to be a 3x3 matrix. So obviously, if I'm only doing a 3x3 matrix, you're probably going to prefer to use just the arrow method for the determinant. But let's practice this strategy. Let me give you a matrix A here. Just want to practice this. So let's suppose the matrix is 2, 1, 3 on the first row. Second row is -1, 2, 6. And the third row is 4, 1, and 12. Okay. And the question is going to be use EROs to find the determinant. Again, we could use the arrow method. We'll get the answer very quickly, but I want to try this one with EROs in case we had a larger matrix and really wanted to get more zeros into it. Okay, so let's do this, guys. Let's actually start with our good old classic chain of EROs. So I start with A, and can somebody recommend a good ERO to start off with here? Joel.
8.
Of course, that's fine. You could do that. I'm very rarely adding lower rows to upper rows. It's not something I like to do. It's generally when you're doing this process, you're adding multiples of higher rows to lower rows. So if we could try to do that, it might be a little better. Brandon? Yeah, I would permute rows 1 and 2 as well, because I want to get that 1 up into the upper left corner. So the first row then becomes -1, 2, 6. The second row is 2, 1, 3. And the third row is 4, 1, and 12. So I would probably do that. And I know that technically a -1 is not a pivot because pivots have to be 1s. But for the time being, I can just leave that as sort of where my pivot is going to end up. Okay. From there, can somebody suggest an ERO to take me to the next step? And what was your name again?
Edith,
Edith, go ahead.
you add rows 2 and 3 times -2.
Okay, I could do A23 of -2. Personally, I would probably use row 1 on both of the lower rows because that's a 1. Guys, that 1 is really your best friend. And in fact, I think what I'm going to do is start with that, if that's okay. So I'm going to do the A12.
-2.
Actually, A12 of 2. Because there's already a minus here. So 2 times the first row, I'm gonna add that to the second row. So this leaves the first row the same. But I'm taking 2 times the first row and I'm adding it to the second row. And if I do that, the second row will become 0, 5, 15. Okay. And what else could I do at the same time? Brandon? A1, 3 of 4, exactly. So I see the -1 and the 4 here. So if I take 4 times the first row and add it to the third row, I'll get 0, 9, and 36. Okay, yeah, I like that. The first column is looking pretty good now. Okay. All right, so far so good? Do we have a suggestion for another ERO now? I gotta play this game a little bit longer.
Could you do M of 1/5?
So for the row 2,
Yeah.
right, so M row 2 of 1/5, because he wants to make this into a 1 here, right? So I'm gonna multiply row 2 by 1/5, so let's just do that. And by the way, there's no need, some people might wonder, well, should I also multiply row 3 by 1/9? There's no need to do that. That doesn't really help you because you're gonna eventually use the second row to zero out the third row below it. So let's just do a 1/5 on the second row and not do any other steps right now. So I'll go ahead and do that. And so the second row is now 0, 1, and 3, and I can circle my pivot here. Okay. And somebody I have not heard from yet today, want to tell me an ERO that might be a good next step? Yeah, Oscar.
Could you add row 2 and 3? And look at the multiple of -9?
Nice. Let's use a multiple of -9 on the second row. Let's add that to the third row. And that will give me the same first 2 rows, but the third row will become 0 and 0. And then if I take -9 times 3 and I add that to 36, I actually get 9 here. Okay. Now, technically, this matrix is not in row echelon form, but there's nothing saying that it has to be in row echelon form when you're done. What it is in
Triangular.
is triangular. It's upper triangular right now. Yeah, this is upper triangular. So I'm going to call this matrix B right here. And the determinant of this matrix, because it's triangular, now we're going to get to the fruits of our labors here. Because it's triangular, what is the determinant of this matrix? Somebody I have not heard from. Yes. -9. So I go right down the main diagonal, I get -9. That's exactly right. Okay, looks good. So guys, here's the deal. This value is not going to be the determinant of the original matrix. We've done all of these EROs in the meantime. So what we have to do now is kind of do the bookkeeping, go backwards through our work to figure out what the determinant of A is. Okay? So if this matrix has a determinant of -9, what would have been the determinant of the matrix right before it?
Positive 36.
No. Take a look at what ERO was done. Take a look at your cheat sheet over here. Which ERO is this? This is the A operation. How does the determinant get affected? No change, right? So whatever this determinant is the same as this determinant. Is that what you were going to say, Brandon? Okay. Yeah, there's no change there. There's no change. So that determinant is -9. Okay. If this one was -9, let's go back to the one right before that. What would have been the determinant of this matrix right here, do you think? Brandon. -9/5. People like that? Yeah.
-45.
-45 is actually the correct answer. This is a tricky step. I want to point out that when we are tracing backwards through our work, we have to actually recognize that if we were going from this matrix back to this matrix, we would have been multiplying row 2 by 5, not by 1/5. So this reciprocal issue sometimes gets people tripped up a little bit. we are currently trying to trace from right to left. And so when we did this ERO, of course, we were going from left to right. But I am now going backwards through my work, which means I have to sort of undo the ERO that I had done earlier. And that would be, instead of multiplying by 1/5, now we're gonna multiply it by 5. Yes, Steve?
So if you're multiplying by 5, you would have to divide by 5.
Right, if we had multiplied by 5 going this way, then going back that way, we would have multiplied by 1/5. Yeah. So this is the only ERO that kind of causes us that problem as we go through it. So this one is -45.
But if you're multiplying by 5, but it's saying to row 2, so why is it 45?
So
Unless I'm missing something.
just this, right? So if I multiply a row through by a constant, the determinant gets multiplied by that constant. So if I'm going from right to left, technically, I am multiplying by 5. So I just take this number, multiply by 5, I get this number.
Okay.
Yeah. Now, if this one is -45, let's go back. What would this one have been? One more time. Also -45, that's because the A operation has no effect on determinants, right? So nothing happens there. And if this one is -45, then can we get to the final answer then? What would be the determinant of the original matrix A? 45, so there's a sign change on the P operation. So this one would be 45, and that would be my answer.
On the
Caesar.
matrix step where we multiply by 1/5,
Yes.
and then you said not to multiply by 1/9 for that bottom row to get that into upper triangular.
I'm just saying I wouldn't recommend
You
it.
did that so we would avoid that step going backwards.
A little bit, but also it's just an unnecessary ERO that just makes more work for yourself. It doesn't actually save you anything. So it is tempting to turn this into a 1 instead of a 9, but if you did that, you still have to do another A operation here. So you're just compounding your workload by doing that. It's not that it's wrong, it's just a little extra work. Yeah. What do you guys think? I should mention that you can use this strategy sort of in combination with any other method that you know. There's nothing that says you have to go all in on doing EROs all the way to the triangular form. So you could have started with this original matrix, and you could have maybe done EROs only until here. Right, and said, that's good enough, I've got a few zeros, I'll just find the determinant of this matrix directly by using the arrow method or cofactor expansion or whatever have you. So you could have just said, I'm stopping here, let's calculate this determinant. Admittedly, I wouldn't have a triangular matrix at this point, so I wouldn't be able to just use my formula there. But this one's not very hard to just directly calculate. And then you could say, all right, from here, then I only have to trace back this far, right? So you can do that. If you've got a whole chain of EROs, you might realize after a while, okay, I don't have to like go all in on bringing it to a full-blown triangular form. You can go as far as you want from left to right here and stop and say, all right, I have my answer. Now I'm going to trace back. Yeah, so that also works. Okay, good enough? Sweet, okay. Well, I've listed 3 important properties about determinants, which are the effects of those EROs. Turns out there's a bunch of other properties of determinants, and before we take a break today, I'd like to write them down. So let's do just a quick list of some other properties about determinants, and then I will feel pretty good about this little topic, okay? So some more properties of determinants. And again, when I'm making this list, I'm probably not going to fully explain every single, I mean, like, I'm not going to justify all these things. I just want you to be aware of them. So I just want to write them down for you. So I'll just call this next one number 4. So 1, 2, and 3 are these. And I'm just extending my list now. So you might wonder, so if A is n by n, then you might wonder, what is the determinant of, let's say, k times A? So this is going to be the first one I want to talk about. How do we find the determinant of k times A? Does anybody think they might, this one we can justify. Does anybody think they might know what the correct formula is for this? If I multiply a matrix by a constant, how we get the new determinant? Yeah, Arnav?
Determinant of K times determinant of A.
Well, K is not a matrix, so I don't want to talk about the determinant of K. K is just a number here. Yeah.
K times determinant of A.
This is the popular answer, is that you're just gonna pull out the K. Is that what you were gonna say, Brandon? Okay, it's very popular. Unfortunately, it's not correct. What is wrong with that? What you actually want to think about, guys, when you multiply the entire matrix by K, you're actually multiplying row 1 by K and row 2 by K and row 3 by K. Every row, every entry, right, gets multiplied by K. Well, that's actually like doing this ERO to every row. So I multiply the first row by K, the second row by K, the third row by K, every row by K. Guys, this should be K to the N. It should be K to the N times the determinant of A, because you have N rows in your matrix, and every one of them, right? Every one of them picks up a factor of K. This is an easy one to get wrong. And so once you are aware of it, I'm sure you'll get it right. It's not a hard formula. But it depends on the size of the matrix, actually. Okay, so that's something to keep in mind. All right, let's do another property here. Number 5. Number 5 is, what would happen to the determinant if you transposed a matrix? And this one is not as obvious, I would say. It turns out that transposing a matrix has no effect on the determinant. No effect at all. So that's a safe thing to do. It doesn't cost you anything. So you can transpose rows and columns for free. All right, let's do another one. Let's talk about the determinant of A times B. So if I had 2 matrices that I was just multiplying them together, what would you guess the formula would be if you didn't have ever seen this before and you were just throwing out a wild guess? What do you suppose the answer might be? Yeah, the determinant of A times the determinant of B. Good news, that's the right answer. Okay, so this one is just determinant of A times determinant of B. Now, I should mention, guys, every time I have the word determinant in front of something, what I'm actually looking at that point is just a number. It's just a number. So remember, I was always making a big deal about how you cannot switch the order of 2 matrices. That's still true, but if I'm looking at these matrices on the level of determinants, these 2 could be switched. So this is just a number, this is just a number. So it's the same as determinant of B times determinant of A, which could then be rewritten as determinant of BA. You see? So I can't switch the order of AB with BA, but the determinant of AB is the same thing as the determinant of BA, because those are just numbers. And with numbers, you can get a little sloppy. Okay, let's do another one. Number 7. What else have we learned about? How about inverses? The determinant of A inverse. This would be a nice one. Of course, this doesn't apply unless the matrix is invertible. Does anybody have a wild guess what the determinant of A inverse would be as a formula? Aiden,
1 over the determinant of A.
you got it. It's 1 over the determinant of A. It's a good guess. It's exactly right. Of course, you always get nervous if you could possibly end up dividing by 0. But actually, if the determinant of A was 0, then we wouldn't even have an A inverse at all. So it wouldn't even come up as an issue, right? So that's important to keep in mind. Okay, so far is everybody with me? So far, so good, I think. I have one more thing to say about this, which is number 8. And I'm going to write it, actually, I'm not going to call it number 8. I'm going to call it a warning. Because this is one that you have to be careful about. And that is, you're probably wondering, well, what about the determinant of A plus B? If I add 2 matrices, can I say something about the determinant there? It turns out that you cannot. This has no formula. It is not the same thing as determinant of A plus determinant of B. It doesn't work that way. And in fact, one of your true false homework items for tomorrow's assignment, I'm going to just do it right now. So this is just an example that goes with this. This is 3.1 part E from the true false. It actually asks us, and so this one is actually false. I'll just tell you now, it's false. What the statement says is determinant of A plus B equals determinant of A plus determinant of B. That's the statement that they're trying to trick you into believing, but then it is not actually true. It is actually not true, and let's be very clear, it is not the case that the determinant of A plus B is the same as the determinant of A plus the determinant of B. How would you convince, remember on the true false items, guys, you need to give me a little reason or something that convinces me that you've thought about it a little bit rather than just writing down that it's false. If I want to convince myself that this is false, all I really have to do is make my own example. I just have to make an example that shows this. And if I was going to make an example here, what size matrices might be kind of convenient to work with?
2 by 2.
Let's make them small, guys. Let's make them 2 by 2, yeah? So let's do that. And let's just see if we can make up an example here. Let's see. Isaac, what are your 4 favorite numbers?
1, 15,
Oh boy. 4.
2.
Okay, great. So there's one matrix right there. That sounds good. Stephen, what are your 4 favorite numbers?
0,
0,
1,
Mhm.
0.
0, 1, and 0, and 1. Okay, great. Let's just test this out. Let's just test this out. The determinant of A using Isaac's matrix, I'm just going to do the AD minus BC equation. So this is 2 minus 60, which is negative 58. If you don't like these big numbers, you can blame Isaac. Negative 58 for the determinant of A. Let's do B. What will be the determinant of B here, by the way? AD minus BC is definitely 0. All right, now let's add A plus B. Let's actually add this together here. Just want to see what we get. If we add the 2 matrices together and we just do that slot by slot, we're going to get 1 and 16 and 4 and 3. And let's work out the determinant of A plus B and see how that jives with what we've already calculated. So in this case, again, we have to do AD minus BC. 1 times 3 minus 16 times 4. So that's 3 minus 64, which should be negative 61. And as you can see, negative 61 is not the same thing as adding negative 58 with 0. So this is a good example that shows that's a false statement. So you can put this on your homework if you want, or if you want to have more fun with it, you can make your own example for that particular item. Okay, so far so good? Makes some sense. Ryan?
Yes, so Professor, for the homework,
Yeah.
if one says false, because we already know that the determinant of A plus B has no formula, would that be wrong?
I would prefer to see an example. I mean, you could say, from Dr. Annan's lecture, there is no formula, but it's almost just sort of stating what's already, I mean, it's sort of like just stating it's false because it's false. It's not really giving me like something I can sink my teeth into. I prefer something like this.
So we can't really say that this is known by necessity, right?
I mean, you can say it's known by something from class. If that's the case and you write that down, it's totally okay. But I just think it would be better to put an actual example down here.
That means the definition.
You could even use the definition, but that's gonna be much messier. Like I don't wanna, I'd really rather not have to like, so you're saying I could put A, B, C, D here and then have the general 2x2 determinant formula and then do the same thing again. And then there was somebody in my office hours who showed me that and they did do it. It's just more writing, it's just more work. You can, when something is false, guys, you can convince me with even one example. So if I say all Saturdays are sunny, right? And you want to convince me that that's wrong. You don't have to like do some general thing. You just have to find a specific example of a Saturday that's not sunny and it's a false statement then. Yeah. So that's good. Sorry, while we're at it, we'll take a break in just a minute, but before I do that, I see that number 32 is on the board over here from the section 3.2. This would be a great time to do it because it's right in line with all of these properties. So let's do that problem. 3.2, number 32 from the homework that's due tomorrow night. What it says is, so they give you this matrix A, which is a 2x2, kind of a standard form here of A, B, and C, B. And they said, assume that the determinant of A is 1. Okay. And then they give you a slightly different matrix. And then they try to ask you what its determinant would be. So let's write it down. So let's let B be equal to the matrix negative B, negative A. And then the bottom row is D minus 4B and C minus 4A. And so this is a homework problem for tomorrow. It's near the end of the assignment, actually. And they ask you to find the determinant of B. Okay. Well, I'm going to do something I don't normally do, which is I'm actually going to solve the problem 2 different ways. And you can kind of take your pick which way you like more. But I think it's instructive to see sort of 2 ways to do this. So maybe I'll start with method number 1. You can kind of decide for yourself which way you like better. You can also write them both up if you want to. But method number 1 is to just use the 2x2 determinant formula directly off of B, right? So the method number 1 would be, okay, for the determinant of B, I just take, the upper left corner, which is negative B, times the lower right corner, which is 4 minus CA. And then I subtract the upper right corner, which is negative A, times the lower left corner, which is D minus 4B. So this is just using the classic 2x2 determinant formula. And what you would do with this is literally just kind of turn off your brain and just run with the algebra, right? Just kind of multiply it out. Negative B times C, yeah. And then we've got a double negative, so it's a 4AB, I believe. And then we've got a plus AD. And then it's actually a triple negative on the 4AB there at the far end. So just kind of, expand it all out. You just have to be a little careful with your signs. And what you notice is that the four ABs actually cancel. And the only thing that's still here is AD minus BC. Well, AD minus BC would have been the determinant of the original matrix, which was given as 1. So this would therefore just be equal to 1 in that case. So the determinant of B is the same as the determinant of A. This is kind of the what I'll call the no-brainer way to get the determinant. You just use the little 2x2 formula, just do some algebra, and it simplifies really nicely. But there's another solution that is kind of instructive, so I like to just show really quick if I could. And then you guys can decide which one you like better. See, the thing is, with using the 2x2 determinant formula, right, you're thinking to yourself, well, if these matrices were 4x4, that would have never worked. Right? If it was a much larger matrix, we don't have a nice formula and we wouldn't have been able to do this. So the question would be, well, what would be something that would be like more sort of broadly applicable? Like what kind of a strategy could we do that would be more broadly applicable? Well, here's what we can do, guys. Somebody came into my office hour to ask me about this question also. And what they noticed was it looks like we actually sort of switched the columns here. Because see where the A and the B are, and down here the B is on the left and the A is on the right. It looks like the columns have been switched. Now, I didn't say anything about column operations. I only been talking about row operations, the effects of the EROs on the determinant. I didn't say anything about doing column operations, so technically we don't have that. But we have a way of turning rows into columns and columns into rows. What's it called? Transpose. Transpose. If you transpose a matrix, which by the way has no effect on the determinant, you will switch the rows with the columns. So if I actually, I'm not going to use a twiddle here because I'm not actually doing an ERO. I'm going to take a transpose on this thing. And so the transpose of A would be the first row becomes the first column and the second row becomes the second column. It would be something that kind of looks like that. And now I can do EROs. So for example, now if I wanted to switch, so I noticed that I kind of wanted to switch the columns here, but I couldn't. But now that I've switched the columns to rows, I can do the permuting of the rows. That would be okay, right? So let's just check this out. If I permute the two rows, then this is a B and a D, and this is an A and a C, right? Ooh, okay. So then what I can do is I can transpose back. This is clever. I can transpose it back now. Take that first row and switch it to the first column, and take the second row and switch it to the second column. I can definitely get away with that. Okay, so I'm mixing EROs with this transpose idea so that I can tweak the columns too. All right. Now from here, I can kind of just look at what B is, and I can say, well, what EROs would take me from that matrix I currently have to this one? Can somebody tell me? Okay, good, thank you. Yeah, I can multiply the first row by -1. So that's another ERO. Multiply row 1 by -1. So then I'll have negative B, negative A, and then the second row stays the same. All right, and is there one more ERO that I need to do to get to the matrix B? Brandon? Add row 1 to 2 with a multiple of 4. So 4 times the first row, add it to the second row. I love it. I love it. And that gives me B. So now, guys, here's the interesting thing. This time, we are not going to trace through our work backwards. This is the part that always throws people off. We're not going to go backwards through this work. We're actually, because we know this determinant is 1 already. We're actually starting from the beginning, and we're going to go forwards through our work to get to B, you see. So unlike the one that I did a few minutes ago in the example, this time we are really going forward. So, if this determinant is one, okay, you guys have to help me now. What will be the determinant of A transpose? It's still equal to one because the transpose has no effect on the determinant. Exactly. What about the next matrix? After I permute rows 1 and 2, what will the determinant become? -1, because according to the very first property over there, permuting 2 rows brings in a sign change. If that one is -1, what will be the determinant of this matrix here on the far right? Stays the same, it doesn't change, so it will stay as -1 because we're transposing. Transpose has no effect, right? Okay, if that determinant is -1, then what will be the determinant of this matrix right here? If we did this ERO, that meant we multiplied through a row by -1. So it's going to be a sign change, so it's back to +1. And then the A operation, does that do anything? Not if you believe property 3 over there. That has no effect, so this determinant is still going to stay as 1. And that's the same answer that we got doing method 1. So this is a little more sophisticated approach using the properties. But if I had a 4x4 matrix where I didn't have like a formula I could crank out, I might still be able to make this kind of approach work, you see. And so it's kind of nice to see that there is another way to do it. Yeah, okay. Yeah, Stephen?
So for going from A to B, you said we went forward this time.
We did.
And so could we say, since we were already working backward, that could be the reason why we're going forward this time instead of how we usually go from like B, for example, going back to A?
I think the key question actually is, am I going forward or am I going backwards? Are you starting with a determinant that you do know and going to one that you don't know? That's what we're doing here. Or are you starting with a matrix whose determinant that you don't know, which was that 3x3 example from earlier, and EROing the heck out of it to bring it to a matrix whose determinant we do know? In that case, you're reversing the process and you're actually going backwards through your work. Yeah, so that's something important to identify if you're going to use this strategy is, are you going forwards or are you going backwards? And the way to answer that is to ask yourself, is the first matrix that I'm looking at a matrix whose determinant I already know, or is it a determinant that I'm trying to find? Okay, so I think it'll play out pretty naturally when you're doing these problems, because you'll be like, oh yeah, I don't know what that determinant is. I guess I better go do some EROs and start from the back and then go backwards. It's kind of just, it's very organically generated as a solution that way. So we have learned how to find determinants of matrices. We've learned quite a few properties of determinants with one red flag here, be careful about. But we've learned quite a bit about how this whole thing works. But there is one thing that we really have not done a very good job so far of addressing. And that is, who cares about determinants? I keep saying up with determinants, right? And I'm not really giving you a strong case. I mean, I've talked about the invertible issue. Okay, so a matrix is invertible if and only if the determinant is not 0. But is there anything else? Is there some geometry? Is there maybe a way to find the inverse using just determinants and all of that stuff? So if I have piqued your curiosity, all you're going to have to do is wait 10 more minutes. And when we come back from the break, I'm going to go through some of these other important things about determinants with you. And it's pretty much going to finish almost all of the rest of the material before next week's test. So let's take a 10-minute break though right now. We've been going for a little while. In 10 minutes, we'll talk about those issues.
Professor, when you multiply, right, when you did the M operation over there, you have that determinant B times, where's that?
K is this.
So which is the -1?
Yes.
It's
not negative.
So when you do this,
Okay.
Yeah, like, when you do, like.
It is, yeah, switching those off, yeah, there definitely be some that's gonna happen.
So.
Let me take a 10-minute break, I'm gonna think about that one.
Permanent, it's like, right? But. Yeah. We have to say. But they don't, okay, and when you. You're three numbers right here. Saving. Okay, everybody back. Let's say this was fine. Now. What happens to the last here? So we're at negative. These two. Don't do anything. And they don't do anything. So we use it. Now, still, so we're still negative 45. That's something that we want this original.
Plans for the weekend?
Yeah.
Studying for this.
Oh, exactly.
There you go, that's right. Yeah, I mean, again, I would probably give a specific example. We'll show something like that, because you're saying in words the right thing.
Yeah.
But then there's nothing more convincing than just showing like a specific numbers that kind of illustrate something. Everything good with your car now?
Yes.
I passed 200,000 miles in the car last week. Yeah, I've had it a long time. That's because I drive it all the time in Colorado. And then during COVID, I even drove it like cross country to do stuff because I didn't want to fly. So I put a lot of miles on the car. I like road trips. So I tend to drive to Arizona and find some mountain and drive back. I do this all the time.
What years are?
It's a 2017, it's a Toyota Corolla, so it gets great gas mileage. It gets really good mileage, and those cars are just like unstoppable. Like they never break down. Never had a problem. The only thing that ever happened was one time my tire light gauge is not really working right. If it gets too cold outside, it thinks my tires are flat, even though they're not. But that's the worst thing that's wrong with the car like that. Everything else still works. It's so good. Uh-huh. Oh, wow. That's incredible. Yeah, I posted up on my social media. I said, "Oh, my car is 300,000." And people were saying, "Oh, go for 300,000, go for 400,000." I'm like, "Oh my gosh, I don't know about that." We'll see. Yeah. But yeah, I've only owned 2 cars in my whole life. Yeah, I had a Honda Civic, and I had that one for 14 years or something. I never even owned a car until I was done with grad school. So I kind of got a late start on cars. Some people probably have more cars in 2 years than I've had in my whole life. What's that? Oh yeah, I've been to every state. I've climbed mountains in almost every state.
Hey, what do you think of the?
So during COVID, I wanted to climb Mount Rainier, which is up in Washington, and I was over in the Midwest because that's where I was doing my remote work during while we were shut down. And so I drove all the way to Washington rather than get up. I mean, I didn't want to get sick because I was about to climb a mountain.
Have you guys started?
So I just decided, all right, I'm just gonna drive it. So that was over 3,000 miles round trip. I had to drive both directions.
How long did it take you to get there? Or how many days did it take?
I think for that I took 2 days, but you might be surprised that normally I drive from Los Angeles to Denver in 1 day. It's 17 hours. I get up like at 6 a.m. and then I just drive like crazy. You can go 80 miles an hour across Utah. Like there's nobody there. So you just go really fast. And then because I live in the Denver area in the summer. So yeah, I've done that drive many times. 17 hours in 1 day. But Mount Rainier took 2 days to drive there. And I had a cat back in those days, and the cat would get so good. Like the first time I took her on that drive, she didn't like it, but then I don't know, they're pretty smart. After 2 or 3 years of driving my cat back and forth between California and Colorado, she'd get in that car, and within 10 minutes, my cat sort of knew, okay, today's our big road trip day, and you just curl up in my lap for 17 hours of driving. It's great.
Would you like, drink like crazy amount of caffeine?
No, caffeine does nothing to me. No, it makes no effect. I crank up music really loud, and then I just sort of know how to power through.
You don't have like favorite spots that you like to stop at, or?
I'll stop at a rest area if I need to and take a little nap, but I don't stop very much. I kind of try to push through just to get there. Yeah, I
What
know.
type of music is it like?
It's up, you know, it's upbeat, it's loud, it's drums and guitars and all that kind of stuff.
Doing 17 hours.
I do. I'll get out of the car and I'll be like, oh my gosh, all the blood is in my feet because I've been sitting all day. Yeah, I have to kind of like, you know, wobble to the front door of my house.
Like 2 hours. Like my.
See if I can keep my balance or whatnot. Yeah, it's a long drive. I'm not planning to do this too many more times. Some point I'm just gonna
What's a good starter hike?
relocate. What's that?
What's a good like starter hike for here in California?
Oh, let's talk about that later because you could get me going all day on that. I have done so many hikes. There's a lot.
Have you ever been to Yosemite?
I've been to all but 4 of the national parks in the country. 2 of them are in Alaska that I didn't go to, and then there's one that's out in the South Pacific over by Australia. Yeah,
What's your favorite?
my favorite national park?
Yeah.
Oh, Rocky Mountain National Park in Colorado. Because it's right next to where I live in the summer and I go hiking every day. And I love it. So it's like super, super fun.
Have you seen like?
But I do like Yosemite. Yosemite is really nice too. Okay, we better get started here, guys. I'm sorry. I would rather, well, no, I shouldn't say that. I would almost rather talk about mountains and climbing, but I also like to talk about this stuff. I'd like to get back on track because I only have about 20 minutes here. And I want to be mostly done with this material, so I don't have a lot to do on Tuesday other than review. This is another problem from the homework that I thought we'd do together because it has some instructive points to it. There's a linear system here. So this is number 22 from section 3.2. They give you this linear system, and I'm just going to remind you from chapter 2. Well, actually, I'd like you to remind me. What are the possibilities for how many solutions a linear system potentially could have? Somebody besides Brandon. One solution or no solutions or infinitely many, right? So every system, as we learned, and it all comes down to the pivots, the way we talked about it in chapter 2. Every system has either no solutions, one solution, or infinitely many solutions. And generally, the first thing that you would do to decide which case you're in is to write down your augmented matrix. So I'm going to do that here. Notice there is a K in this system, but I'm going to go ahead and just write down this system. Just by put all those numbers into that matrix there. Now, I want to remind you that the case of no solutions, if you remember, this happens when there's a pivot in the far right column, right? So pivot in far right column. Well, what I want to ask you is, could that ever happen here? Can you get a pivot in the far right column by doing EROs here?
Yeah.
If this entire column is zeros, if I permute two rows,
Yeah.
still all zeros, right? If I multiply a row through by a constant,
It'd be 0.
all zeros in the last column. If I add a multiple of one row to another, all zeros in the last column. So for this system, for this problem, because these are all zeros, you can't have no solutions. And if you don't like that reason, another reason why I can tell you that you don't have no solutions is I can actually give you a solution that I know will work, which is if I put 0 for all of the unknowns, it will check off all 3 equations just like that. Yeah. So this system does not have no solutions, which means it either has one solution or it has infinitely many solutions. And they're asking us, under what situation would there be infinitely many solutions? Can somebody tell me, like, what would differentiate these two cases? Is there a scenario that would tell us that there's one solution, for example? Yair? I'm coming to that because this is, after all, in chapter 3, so it has something to do with determinants. But specifically about the matrix, yes?
If there's a row of zeros.
If we do the EROs and we get a row of zeros, then we would have infinitely many solutions. Of course, I'm not going to do EROs here because I'm doing chapter 3. I'm going to use determinants is actually how we're going to do it. But what I'm really looking at here, guys, is that there would be one solution if the determinant is not 0. In other words, sorry, let me say that differently. One solution would be if A is what kind of matrix? Invertible. If that's my capital A, then A is invertible. You remember the invertible matrix theorem from Tuesday? A is invertible. The very next statement was, oh, your linear system has one unique solution, right? So if there's going to be one unique solution, that coincides with A being invertible. So what's the opposite scenario? Well, infinitely many solutions. This would be A is not invertible, i.e., the determinant of A does equal 0. So if I could, I'm not going to finish this problem right now, but I'm going to tell you how to finish it. Just take this matrix here, guys, 3 by 3 matrix. You can use the arrow method, whatever you want. You can ignore this now. Ignore that far right column. Just take this 3 by 3 determinant, set it equal to 0, and solve for K. because that's what they're asking for. For what values of k would you be in this scenario over here, right? In the scenario of infinitely many solutions, well, it should be that the determinant does equal 0. So just take this determinant using the arrow method. It'll have k in it as you work that out and set it equal to 0. Okay, I'll let you guys check it. I think there's 2 values of k that you're going to come up with here. Okay, so I wanted to do that one because it's kind of a nice application that ties in with some stuff we've talked about in the past. What I want to do in the last part of our class today, guys, is kind of work on this question of what is the importance of determinants. Like, why is it important? What is it good for? And the first reason, there's going to be a list of 4 things. I'm going to give you 4 things here. The first one is, it is a test for invertibility. And this we already talked about. This is just, A is invertible, right? If and only if the determinant of A is not 0, right? So that's something we mentioned even on Tuesday. I'm just reminding you that's kind of where this whole chapter 3 got started. This is the up with determinants perspective that I'm talking about. We care about determinants because we can test if a matrix is invertible. But I'm going to add 3 more things to this list, 2 of which we need to do by next week's exam. The last one we'll hold off on. So the first of these is number 2, is something called an adjoint method for A inverse. An adjoint method for A inverse. And I'm going to write down a formula right now that you probably won't understand immediately, but we're going to explain it in a minute. And that is that this is a formula for finding A inverse without using EROs, without doing the Gauss-Jordan method, which we already have, right? But let's say you want to find A inverse without having to do any EROs. There's actually a way to do it using determinants instead. And here's the formula. You're going to take 1 over the determinant of A. Now already we get nervous. So is this going to be 0 on the bottom? Oh, wait a minute. If we're finding A inverse, then the determinant must not be 0. Okay. So we have that, and we need to take that, which is just a number, and multiply it by something I have to explain in a minute called the adjoint of A. That's written ADJ of A. So this is a formula that we can use to actually find the inverse of A by using determinants. And again, I am not ready to sort of call this done. I have to explain adjoint of A for you in just a minute. The other thing, number 3, so maybe what I should be doing here, guys, I should be saying on these notes here, see below. Okay, because we still, at least for numbers 2, 3, and 4, we need to talk a little more. But let's at least get it summarized in one nice place here first. The next one is something that I didn't, in the past, I was not including it in Math 250B, but then all of my former 250B students keep coming back to my office to say, my professor is talking about something called Cramer's rule over in the engineering college. And I'm like, oh, I guess I didn't teach that. And I had to kind of feel guilty about it for a minute. So I'm not going to feel so guilty anymore because I'm actually going to cover it with you here. Cramer's rule, it's called Cramer's rule. And what is that for? Well, that's actually a way of solving a system of equations. So AX equals B. It's a way of solving this system for the unknowns. And again, I'm going to write down a formula that needs to be explained below. And essentially, what are these unknowns going to be? Well, let's just figure out like what is the jth unknown. Remember, if A is invertible, that's going to be an assumption. This is A has to be invertible. There will be a unique solution for all of these x's. And here's what it is. It's a fraction. And on the bottom, we put determinant of A again. Again, if A is not invertible, you can't do this. You can't divide by 0, and there is no Cramer's rule. Cramer's rule is only for an invertible coefficient matrix. And then what goes on top is something that I'm going to write as determinant of B sub j. So B sub j is a matrix that I have to tell you what it is. So again, see below. All right. And then the fourth point is going to be, this is the one that I'm not going to worry about so much for, at least not for this chapter 3. But it turns out that there are geometric, I think this is what somebody earlier was suggesting, geometric interpretations. Like it means something in terms of like specifically area and volume, right? So area and volume interpretations, and this would be for, we're really going to mainly use this one for 2x2 or 3x3 matrices. So if the matrix is larger than that, then geometry gets a little hard because you can't visualize anything in 4 dimensions or 5 dimensions. But at least for a 2x2, there's going to be some interpretation that determinant represents some area that we can actually draw. And for a 3x3 matrix, that's going to coincide with measuring the volume of some solid that is based on the matrix. So I'll come back to number 4 whenever I have some free time later. That one is not so critical in the immediate future, but I'd like to at least get through number 2 here right now. It's pretty quick. The only thing about number 2 that I have not yet explained really is what is ADJ of A. So I want to talk about that. Okay, guys, so up with determinants. Up with determinants. They allow us to do lots of good stuff. That's kind of my message here. That's my message. There's lots of good stuff we can do with determinants. So let's go back now and fill in the gaps here on number 2. This, as I said, does not take very long at all. So I do need a definition. And the definition is so the definition, guys, if every entry of capital A is replaced by the corresponding cofactor, okay, this is a definition. If every entry of A is replaced by the corresponding cofactor, we get the matrix. It's called the matrix of cofactors. It's called the matrix of cofactors. That's going to be denoted as an M sub C. So I'm going to do an example in a minute, but basically if I give you a matrix and I just calculate all of the cofactors, that's called the matrix of cofactors. Okay? And then the next definition that we need is the adjoint of A. So the adjoint of A, and this is written ADJ of A, the adjoint of A, which is the ADJ of A, which by the way is the thing appearing in the formula over there, is simply this. The adjoint of A is, as it turns out, it is just the transpose of that matrix of cofactors. So that's it in a nutshell. If you want to find the inverse of a matrix, you can find the determinant of it, because that's in the denominator over there. And then I'm looking at that second box on the far right wall. The determinant is in the denominator, and what's in the numerator is the adjoint of A. And what is that? It's just the transpose of this matrix of cofactors here. That's all it is. Let's just do a quick example, and I think you'll get the idea. Okay, so do an example. Let capital A be equal to this matrix. I'm just going to do a 3 by 3. Just going to do a 3 by 3. So 2, -3, and 0 on the first row. And then on the second row, 2, 1, and 5. And on the third row, 0, -1, and 2. Okay, so it's a 3 by 3. And what I want to do on this example is find A inverse. Now, of course, if you wanted, you could use the Gauss-Jordan method. You could remember how that works. You could augment this with the identity matrix and do EROs until you get the identity matrix on the left side and the A inverse on the right side. We learned that previously, but I would like to find A inverse this time using the adjoint method that we've just explained here in number 2. Okay, so with 5 minutes or so, I should have no trouble with that. Okay, the lion's share of the work on this is to just get this matrix of cofactors. Once you've done that, you're basically almost done, right? You're almost done. Well, I guess we also have to find the determinant. Also have to do the determinant. I'm going to save that. For the determinant here, I would just use the arrow method. Okay, actually, so let me just tell you what it is. Save you a little headache. Note that the determinant of A equals, and I'm just going to put the word check here. So you can check this with the arrow method if you want to. Turns out it's equal to 26. It's equal to 26. So we can just feel pretty confident with that, just using the arrow method. That's going to be the denominator. Now, what we really need to focus on is this matrix of cofactors. So what is it exactly? It's another matrix of the same size as A was. And what's it say? We're going to replace every entry of A by whatever the corresponding cofactor is, meaning that the 1, 1 entry becomes the 1, 1 cofactor. The 1, 2 entry becomes the 1, 2 cofactor, and so on, all the way through the whole matrix. This is what the matrix of cofactors is actually going to be. It's going to look like that, yeah? So why do I say this is the lion's share of the work? Is because I have to do 9 cofactors right now. Okay? This is a little more work than just cofactor expansion. Remember, guys, when you're doing cofactor expansion to find a determinant, you're only picking 1 row or 1 column to expand them. That's not that many cofactors. Well, here we have to go all the way through the whole matrix and get all of these cofactors, you see. So let's see if we can do it. Can we do 9 cofactors in 2 minutes? I think we can. Let's check it out. What is the 1, 1 cofactor? So to do the cofactors, I'm going to kind of wave my hands here. To do the 1, 1 cofactor, I cross off row 1 and column 1, and I look at the determinant of what's left, right? What is the determinant of the 2 by 2 matrix that you can see right there?
It's 3, right?
What'd you say?
7.
It's 7, guys. 1 times 2 minus 5 times -1.
Oh my
2
gosh.
plus 5 is 7. So I'm gonna put a 7 right here. Clear enough?
Yeah.
Okay. Maybe we can't do 9 of these in 2 minutes. Let's try another one. Let's do the 1, 2 cofactor. I'm gonna cross off row 1 and column 2. Can you tell me the determinant of the 2 by 2 matrix that's showing right now? It's 4, right? So do I put 4 over here? -4. Why do I put -4? The plus minus thing, right? Don't forget, guys, these cofactors have this alternating pattern. I wondered if I was gonna fool anybody. You guys were all over that. That's a 4, but you have to have a sign change there. So it becomes a -4. Okay, let's do the rest of these really quick. The 1, 3 cofactor, what's that gonna be? -2 minus 0 is -2. No sign change on that one. It stays as -2. Okay. Let's do the 2, 1 cofactor. So that means I'm going to cross off the middle row and the first column. What is the determinant of the matrix that's showing right here?
-6.
It's actually -6.
But then it's a 6 again.
But because of the sign change, I have to write 6, not -6. With me? Now the one in the middle, after I cross off the middle row and column, I'm just doing the outside 4 corners. What's the determinant of that?
It's 4.
It's 4 with no sign change, stays as 4, right? Let's keep going, we're almost there. I cross off for the 2, 3 entry, I cross off the middle row and the third column. What's the 2, 3 cofactor gonna be?
It should be 2.
It's going to be +2. This determinant is -2. Guys, I'm just doing these little 2 by 2s in my head, right? It's -2, but I have to change it to a +2. All right. Bottom row, the lower left corner, I have this little submatrix, -15, right? That's -15. Then the lower middle entry, I have 10 minus 0, but I have to change it to -10 because of the sign change there. And then the far bottom right corner, I have 2 minus -6, which is 8. By the way, I'm not multiplying these determinants by the entries. When we did cofactor expansion, we were doing that, right? The AIJs got multiplied by the CIJs as I expanded across a row or a column, yeah? Here, I'm not doing that. If I want to know the 3, 3 cofactor, I just do this determinant. I don't worry about the fact that this is 2. It could have been a 3, it could have been a 4, it could have been any number. The cofactor is still 8. Okay, so last thing, this is the matrix of cofactors. So what is the adjoint of A? It's the transpose of that. So let's swap the rows with the columns. First row becomes the first column. Second row becomes the second column, and third row becomes the third column. There is your adjoint of A. And so what is A inverse? One more second, we'll just write it down and we'll be good to go. For the A inverse, now we use the adjoint theorem. So the A inverse, just a second here, I just want to get this written down. 1 over the determinant, that was 26 times this adjoint matrix, which I'm copying down. Am I getting it right? Yeah, -4, 4, -10, and then -2, 2, and 8. Yair, did you have a quick question?
No.
You good?
Yeah.
By the way, guys, it's perfectly okay to leave this 1 over 26 in the front. If you had done the Gauss-Jordan method, if you had done the old method, do you know what your answer would have looked like? It would have looked like this. Can you imagine having to think about these kind of fractions? And not making a mistake, right? Because when you're doing the Gauss-Jordan method, you don't have this nice, clean scalar factored out in front. Isn't this so nice? There's just whole numbers here. There's no fractions in these adjoint calculations. The only place there's a fraction is when you divide by the determinant in the front. But if you did it the old method, those fractions would be living with you all the way through the work. It would be really super annoying. Yeah. Guys, I'm gonna send you a 5-minute video on Kramer's rule. It's a real easy one that you can watch so you can do Tuesday's homework. Tuesday's homework is mostly items 2 and 3 on that list over there. So I'll be around. If you got questions for me, let me know. I'll do what I can to help. That's it for today.
What if we did one of them?
I probably won't have you do submission of notes on that one. I just want you to have something to watch so you can do the homework. Yeah. Sorry.
Where'd you get the 26 from?
Right here.
Oh, okay.
Yeah. Oh, I'm like,
yeah, not useful, yeah.
he finds other workarounds. So like he would do this adjoint method, he would say, guys, let's do the Gauss Jordan, right? And he would be not interested in geometry. He would make the case, this is a linear algebra class, who cares about geometry? That kind of thing.
Did you say that the course that way?
I think it is. I think that linear algebra in the right book is actually pretty hard.
So what about for some?
We actually use that in our 300 level math class.
So what about for someone like myself, like already?
Oh, I'd be fine with it.
No,
But I wouldn't want to teach it.
no, but like, so your preference would be still this?
Oh, yeah.
Yeah, even.
I wrote this book the way I did because I like it this way. Yeah, good question. Good question.